So welcome to this session on convex optimization. So I'm James Kwok from Hong Kong University of Science and Technology. So in this session, we are going to have 5 speakers. So the first talk will be given by Professor Stephen Wright from Wisconsin-Madison.
Thank you very much. Thank you all for coming. So I'd like to talk about the use of dissipativity theory from control as a way of analyzing the convergence of some stochastic optimization methods. This is joint work with Bin Hu and Laurent Lassard, who are both colleagues at UW-Madison. Bin's about to go to UIUC, actually. So I'll start by saying a little bit about LMIs, linear matrix inequalities, and dissipativity. These are concepts from control. Talk a little bit about, in fact, talk quite a bit about how they can be applied to the convergence of optimization methods. And then I'll focus on specifically 3 methods: stochastic gradient, one that's very familiar to everyone, SVRG, I guess almost equally familiar, and Katyusha that we heard about in an earlier session this afternoon. So this is our target problem for most of the talk, the finite sum convex problem, where the G, I'll use G instead of F, I'm not sure why, Bin seems to prefer that, to denote the overall objective. I'll assume that that's strongly convex with modulus sigma, and then it's a sum of n functions fi, each of which is convex, and the gradient of all the fi's has Lipschitz constant L. Therefore, there's a unique minimizer. I'll denote that by x star. And as I said, I'll talk about these 3 methods. Okay, so let me give the control perspective and introduce some control notation here. So it turns out that many algorithms in optimization can be written as a so-called linear time invariant system in control. So I introduce this concept of a state of the system at some time k, denoted by this quantity psi. And then wk is the input to the system. So typically the state will be something like the error in the current iterate, as you'll see from the examples that I give. Wk often contains derivative information that's kind of driving the system towards some desirable state, which in our case is, of course, convergence to the solution. And then A and B are fixed matrices that don't change with each iteration. And so a lot of them, and I'll show a ton of examples, can be put into this framework. And then you can use dissipativity theory to analyze the behavior of the system, as we'll see. That's the idea. And you can potentially also use what you learn from this theory to make different choices of the parameters in the algorithm, line search parameters and so on, and possibly even to get tighter bounds on convergence rates. So here's an example. There's a little bit of an explosion of notation here, but basically what's going on is very simple. This is a classical method, heavy ball. This is from a description in the Russian literature, Boris Polyak's book from the mid-'80s. So heavy ball is one of the canonical momentum type methods for unconstrained optimization. Basically, each search direction is just a combination of a negative gradient contribution, negative grad f, as you see here, and a multiple of the previous search direction, pk minus 1. And this is a pattern that recurs in all kind of momentum methods in one form or another, slightly modified. So this is the formula that fully defines how I get from xk to xk plus 1 in the heavy ball method. Now, if I break down that formula by, subtracting x star from both sides and messing around a little bit, I can write it in the linear time invariant form exactly like this. So I'm defining the psi k to be simply the error at 2 successive iterates x. I'll define the wk to be the gradient at xk. The A is just this matrix here. It depends on the parameter beta. And the B is this matrix here. It depends on the parameter alpha. Okay? So this is an example of how I take a classic optimization method and put it in LTI form. Okay, so here is one of the theorems that I guess this is a definition that drives the rest of the talk, this idea of dissipativity. So I'm going to introduce 2 critical functions. There's the storage function, which given a state, psi, it defines how much energy is in the system at state psi. And the second thing is the supply rate. So this is a function both of psi and the input w, and this defines how much energy is being put into the system, okay? And so we call the LTI system almost surely dissipative if it satisfies this inequality. That is, the storage function at time k plus 1 is less than or equal to the storage at time k plus s, which is the energy that was put into the system at time k. So it's called dissipative because there's a less than or equal to here. It says that the new value of the storage function is bounded above by the current value of the storage function plus S. It could be less than, so the energy could be dissipating. So what we try to do is to prove inequalities like this for different algorithms, different kinds of optimization algorithms. Okay, now you can get a stronger result for that. For some algorithms, you can actually show that the current value of V gets scaled by some rho squared, where rho might be less than 1. And you can prove that's called an exponential dissipation inequality that allows you potentially to prove stronger results that look like linear convergence rates. And actually, my two co-authors did this last year in ICML. They proved an inequality like this for Nesterov's method, and thereby were able to show a linear convergence rate. Okay, now let's talk about supply functions. So I'm going to be looking for all of these different methods that we consider, I'm going to be looking for supply functions of a very special form. It's going to be a quadratic function of the state and the input. So the supply function Sj is fully defined by this matrix Xj. And I'm going to try to do that for as many, supply functions as I can find. And then I'm going to assemble them into an overall S by just taking a positive combination. And I'm going to assume that each of these, in expected value, each of these Sj's is bounded above by this some value lambda j. Okay? So this is all a little bit mysterious, but it turns out that these supply functions often follow very naturally from the properties of the functions that we're dealing with. The strong convexity, the Lipschitz constant on the gradient, all those kinds of things. From those properties, you can construct plausible values of supply functions, as we'll see. Okay, so they're usually just restatements of known properties. Okay, so given that now you've got an LTI that defines the algorithm, you've constructed a bunch of supply functions defined by these xj's for j going from 1 up to big J, this is the critical theorem that sort of drives the rest of the talk. And what it says is that we can find a storage function V, which is also a quadratic form, defined by some positive semi-definite matrix P. So there exists a V with this form, provided that I can find some lambdas that make this matrix negative semi-definite. So I know what A is, I know what B is, they're the matrices that define the LTI. I'm choosing a P, I'm choosing a rho. Rho is the target linear convergence rate I'm looking for. So I'm able to fill in that matrix completely. I know what the xj's are because I'm deriving the supply functions from the properties of the function. So the only unknowns here are the lambdas, and I'm looking for lambdas that make this matrix non-negative. This is a linear matrix inequality. You can use your favorite piece of semi-definite programming software to solve it. So you can just load up your CVX in MATLAB and plug in these matrices and you can solve this problem. So it's very easy to check this condition. The proof that, and provided this is true, then this is what follows. That means then you're able to state that this dissipation, this exponential dissipation inequality holds. And from this you can define all sorts of nice properties of the method. So I've thrown a whole lot of concepts at you, so let's just take a deep breath and summarize what we've learned so far from all this. This is the procedure that we have to go through to analyze the convergence of an optimization method. First of all, we have to write down the algorithm as an LTI. So we have to define the states and the A and B and the inputs, okay? And I'll give a couple of examples of that. Then we have to define the supply rate. So we have to find these xj's that sort of capture the properties of the functions that we're dealing with. Having done that, we choose a P to define the value function. Often that's very simple. It's often just the identity, in fact. And we pick a target linear rate that we're looking to prove about the algorithm. Then we go and solve this LMI and verify that, in fact, the A and the B and the P and the rho and the supply rates all satisfy this property. If they do, then we're able to assert that this inequality holds, okay? And then we take that inequality and we reinterpret it in terms of the optimization algorithm. We're then able to get results about convergence. So this is the overall kind of map of how we go about using these tools to prove convergence results. Now, why is this useful? One way it's useful is that potentially we could do some meta optimization. We could use the fact that the parameters in the algorithm, like step length parameters and so on, as well as this convergence rate, as sort of hyperparameters of this LMI, and we could try doing some meta optimization or hyper optimization of those parameters to try to maybe get a tighter convergence rate or better values of those step lengths. So that's one potential use of this approach. Okay, so I'll give, as time permits, I'll give some examples of of how we apply these tools and how we rederive. In most cases, we're rederiving known results, but also maybe pointing the way to slightly tighter results. So here's the simplest one, stochastic gradient. So stochastic gradient, this is the basic fixed step length stochastic gradient method, where I've got the finite sum. I pick one term in that sum, denoted by ik, at random, uniformly, and I take a fixed step in that direction. So I can write that as an LTI very, very easily. The ck is simply the distance between xk and the solution. A and b are defined like this. They're just the identity, or minus eta times the identity, where eta is the step length. Here's my wk. So I can write down two supply rate functions for this problem, and here they are. And this one simply is a restatement of the strong convexity property. That's all it is. Strong convexity with modulus sigma. And you can show that if you put in these values of psi and w, that basically, this implies this is the same thing as saying that the G has strong convexity. And the second one is a straightforward consequence of all the FIs being having the gradient having Lipschitz constant L. Same sort of thing. So this just captures the properties that we stated back on the first slide about the objective. Okay, so I've got all the tools I need now to, and by the way, in expectation, these are the upper bounds on those two supply rate functions. This one is positive, okay? It depends on the gradients at the solution. This one is 0. Okay, so we've got all the tools we need to plug it into that LMI. And the LMI that we have to solve is we ask the question, are there values of lambda 1 and lambda 2 that make this matrix negative semi-definite? And this is so simple. It's a 2 by 2. So we can actually eyeball a solution. And it turns out you can get a solution provided the rho squared is defined like this, and lambda 1 and lambda 2 are defined like this. You can sit down and, with pen and paper, figure out what this is. Then from the main theorem that I stated a few slides back, if I just write down this dissipation inequality, this is exactly what it is here. And what it's saying is that the expected value of the squared error at iteration k is less than or equal to some constant less than 1 raised to the power k times the initial squared error. By the way, I got this by taking that dissipation inequality and just recursing it all the way back to the first iteration. So there was one more step there. So I've got a rho to the 2k here times the initial error plus some constant, okay? And this is a very familiar result for people who know stochastic gradient. You often see this exponential convergence to some ball around the solution. That's what you get with fixed step length stochastic gradient. So this is a way of recovering the classical behavior of fixed step length stochastic gradient. Okay, so that's the easiest case. Let's take the next easiest case, which is SVRG. So just reviewing SVRG, this is an epoch-like algorithm. It proceeds by epochs. It generates these outer iterates, x tilde, indexed by s. Then within each epoch, you take steps like this. You take m steps, and each of them basically is like a steepest descent step, but it does a little update of the gradient based on some random sampling among the terms in the sum. So this, and it generates iterates xsk. So what we're going to do is use the LMI tools to analyze a single epoch, what's going on inside each epoch. In other words, this recursion for k going from 1 up to m, okay? Reaching the end of the epoch, there are two ways, or there's actually more than two, but we've analyzed two of them. There are two ways to get the next outer iterate, x tilde s plus 1. One is that you just take the last inner iterate from this recursion. The other one is you take an average of all the inner iterates, okay? And we actually get somewhat different convergence results for those two variants. Okay, so what we're going to try to do here is to show that the expected value of the storage function at the s plus 1 outer iteration is less than or equal to some constant nu strictly less than 1 times the expected value at the previous outer iteration. So our target here is to figure out what's an appropriate value for this nu. We want to show a linear convergence rate. And we get that by digging into what happens in the inner iterations inside each epoch and applying this dissipativity theory. Okay, so here's what we need to do to express this iteration as an LTI. This is how we define A and B. This is how we define the state. It's simply the error in the current iterate. This is how we define the input. And you can see that I've just taken this term, I've added and subtracted grad fik of x star. Okay, and this gives me exactly the recursion on the previous slide. Okay, I need some supply rates. In fact, I can get 4 supply rates by digging into the properties of the function that we're dealing with, and also digging in a little bit to the properties of the algorithm. I won't go into the details of this too much, but basically the second one comes from the strong convexity of G. The first and the third, x1 and x3, come from the Lipschitz property and from a co-coercivity property, which you'll find in any convex analysis textbook. And the last one comes from the sampling strategy, which is how sampling is done in this method. So we've got 4 supply functions to play with. Notice, in contrast to the stochastic gradient, 3 of them have an upper bound of 0, which is great because it means we're not putting any energy into the system. But the 4th one has a positive upper bound. But that positive upper bound is going to 0. As the adder iterates converge to x star, that's going to 0. And that helps us get a linear convergence rate, not just linear convergence to a ball. Okay, so that's an improvement. Okay, so this is what we get. This is our LMI. We have to find constants lambda 1 through lambda 4 that make this matrix negative semi-definite. And from that, we're able to deduce, by taking the dissipation inequality, recursing all the way back to the start of the epoch, we're able to show that we get this much reduction over the m steps of the inner iteration within the epoch. Okay, and it turns out, once again, this is simple enough that we can sort of eyeball a solution if we stare at it long enough and go through a few sheets of paper. And here's the solution here. So for a given step length nu, we get these values of lambda, this value of rho squared, and we end up recovering a result, a known result, for the convergence of SVRG. And this is the value of nu. This tells me how much reduction is happening within this epoch. And by appropriate choice of nu and m, we can make this less than 1, okay? Okay, so that's the first option. The second option for SVRG is where you average over all the iterates. I won't go into detail on this one, but there are 3 supply functions here. They all have upper bounds that are positive, but going to 0 as the adder iterates converge. We end up with this epoch-wise reduction in the error in G. And that can, if you mess around with that a bit, plug in this, again, the eyeball solution, you recover exactly the rate in the original Johnson-Jung paper. This expression gives you the epoch-wise convergence, and that's exactly what they got. We didn't do this, but by messing around with this condition some more, you might be able to potentially find better step lengths and get a slightly tighter rate. Okay, and I've only got a minute or so left, I think, so let me talk about Katusha. This case is quite a bit more complicated. In Katusha, you take the finite sum and you add on a regularization term. And most of the Katusha paper assumes that this regularization term is actually strongly convex by itself, although it may be non-smooth. So this is the formula for Katusha. It generates 3 sequences of iterates, not just 1. There are some subgradients here coming from this potentially non-smooth function. So quite complicated. When you write that as an LTI, it's a bigger LTI than we've seen before. Now the state and the input are both 3 and 3p by 3, both have length 3p instead of just p or 2p. The A and B look like that. Now it turns out we get a single supply function. It's fiendishly complicated. It took half a page of the paper to write it down. It involves a 6 by 6 matrix. We're able to show that, again, you can solve the LTI. You can find values of the lambda 1 in this case that basically recover the result in Alan Ju's paper. And in fact, in Alan Ju's paper, he chose the value 1/2 for one of the parameters. We show that, in fact, you've got a little bit more flexibility than that. You can choose it in this range from 0.2 to 1. And the second parameter, tau 1, which shows up, I guess, here, again, you can choose it just to be anything in that range, and you can then recover the same convergence rate as in the original Katusha paper. Okay, so I'm done. There's a minute for questions, maybe.
Yeah, so we have time for 1 or 2 questions.
Yes, very nice work. I'm curious about the fact that you assume that you get a linear time invariant system.
Right.
But the reason why that happens is because you choose the input, WK, to be dependent upon the state.
That's right.
And so dissipativity theory applies typically, or with LMIs and all of that, to LTI systems, and the input is not dependent on the state. So I'm curious as to why what you've presented today applies to that case.
Okay, so I'm not the control expert, and unfortunately the control experts are not here. But so I can't really answer that, except that I thought in most control systems the input was, you know, if you had any sort of feedback control, it's going to...
No, it's not linear because the WK is minus the gradient of the function. And so effectively you get a nonlinear dynamical system, and that can change the stability properties and all that.
Okay, all right. We'll look into that. Okay, this sounds like a discussion for the poster session. Poster 137.
Yeah, so unfortunately we run out of time, so let's thank the speaker again. So the second talk will be presented by Brian from Wisconsin Madison.
Okay, thank you. So yeah, my name is Brian Vanskoy, and this is joint work with Adrian Taylor, who's down in the front row here, and Laurent Lassard. And so in this work, we consider first-order optimization problems where we're trying to minimize f of x subject to x in RD. And the main results are that we develop this automatic way of analyzing first-order methods to solve this problem. And we only have to solve a small semi-definite program. And in some cases, the convergence rate is provably tight, in particular when the objective function is smooth and strongly convex, and our method is iterative and has fixed step sizes. But I'll also show we can extend this to many other cases as well, possibly without tightness in those cases. And this combines several other well-known results, and so in particular the performance estimation problem. But in the performance estimation problem, you have to solve an SDP that the size grows with the number of iterations, whereas our SDP is small and you get this asymptotic convergence rate. And it also generalizes integral quadratic constraints from robust control theory. And the main tool that it uses is this smooth, strongly convex interpolation. And so we're going to be mainly looking at first-order iterative fixed-step methods. And so this is the general method. So the state x is updated with a linear combination of the past iterates minus some gradient, and the gradient is evaluated at some other linear combination of the past iterates. And we call this capital N the degree of the method. So that's the number of past iterates that are used in updating the method. And so our main result says that we have this semi-definite program, and the SDP is a function of the strong convexity parameter mu, the Lipschitz parameter L, the convergence rate that we want to verify, rho, and the step sizes, alpha, beta, gamma. And if that SDP is feasible, then the method converges for all functions in our class with rate at least rho. And I said that this is tight in some cases. And so what we mean by that is that if the SDP is feasible, then there exists a quadratic Lyapunov function which proves the stability. And this in particular is tight. So it's an if and only if condition. And so now let me tell you very briefly what I mean by a quadratic Lyapunov function. So Lyapunov functions are a standard tool from control theory that can be used to verify the stability of a dynamical system. And so you can associate optimization algorithms with dynamical systems where the state corresponds to your iterates and function values and gradient values. And then the Lyapunov function you can basically think of as a function which characterizes the energy in the system. And so you can think of it as this bowl-shaped function which is 0 at the optimizer and grows as you move away from the optimizer. And in particular, we're looking for quadratic Lyapunov functions. And so we look for Lyapunov functions of this form. And so you notice that it's quadratic in the iterates, xk's, and the gradient values, and it's linear in the function values. And we're able to search over this efficiently by solving an SDP. Okay, so let's look at some results here for several different cases. So first we'll look at just some standard first order fixed step methods. And so we have the gradient method, heavy ball method, fast gradient method, and triple momentum method. And so what I'm plotting here is the number of iterations that it takes to converge, which is proportional to -1 over log rho, as a function of the condition ratio kappa, which is L over mu. And so you notice that the gradient method converges very slowly. The heavy ball method, when tuned for quadratics, does not converge in general for strongly convex functions. And then the fast gradient method and triple momentum method get this accelerated rate. Okay, so this is the case where our results are provably tight on these methods, but we can also extend this to analyze many other more sophisticated methods. So for example, we can look at methods with line search or subspace searches. So here's the gradient method with line search, where we just choose alpha at each time step to minimize the function value. And then we can also do the same with the heavy ball method, searching over both parameters alpha and beta and taking the best parameters at each iteration. And so then you get these dashed lines on the curve. And so you notice that the gradient method now converges much faster if you have an exact line search, but you still get the same slope of this line. And the heavy ball method now becomes stable and converges, but still isn't too much of an improvement. Another really interesting method that we can analyze is the fast gradient method. So this is due to Nesterov in 1983, and so this is the version for weakly convex functions and has the time-varying step sizes. And so it doesn't quite fit in our framework, but we can adapt our framework to also analyze this method. And so this method is useful if you're optimizing a strongly convex function, but you don't know the strong convexity parameter a priori, then you can apply this method with fixed restarts, and you can recover an accelerated convergence rate even without knowing the strong convexity parameter. And an upper bound for this was shown by O'Donoghue and Candace. They showed that the convergence rate using the optimal number of iterations before restarting is upper bounded by this number. And so we can plot the number of iterations that it takes to converge for different values of restart using n is 1, 5, 10, 20. And then the dashed line is the upper bound, and the solid black line is just the minimum over each n. So in particular, this work, they only do their analysis on quadratic functions, but using our framework, we're able to actually use smooth, strongly convex functions and come up with an exact characterization of the optimal convergence rate. Okay, so to summarize, presented this automatic method of analyzing optimization algorithms. We only have to solve a small semi-definite program, and this method is provably tight in a limited number of cases, but it can easily be extended to many other scenarios. And so if you're designing a new optimization algorithm, you can, instead of wasting all your time trying to come up with a proof, you can just throw this at it and see whether or not it works well. And if it does, then you can spend the time trying to come up with a proof and use the numerics to also help drive the proof. And if you're interested in running this, we have our code is posted online, so all the code to make all of these figures is on GitHub. So thank you.
So we have time for a question. So can you go to the microphone? Yeah, there. Because we want to record it, yeah.
Hey, Nice work. I'm curious, just like with the Lyapunov function optimization, you can maximize region of attraction. Have you done extensions to optimizing the degree or like the beta and gamma parameters in order to accelerate convergence on a specific class of functions given the SDP Lyapunov constraint of stability?
Yeah, so once you have the SDP, you can do this meta optimization of trying to optimize the step size parameters. So that problem then is no longer convex. So you can't efficiently solve for it, but you can do some search methods to try to find optimal parameters in those cases as well.
And will that hill climbing still retain sparsity in the degree of the beta and the gammas in terms of?
What do you mean by sparsity in beta and gamma?
Not sure, like is just like with a reduced order control, is there an advantage of less or more? I don't know, honestly.
I mean, so you have to fix like the number of betas and gammas that you're searching for ahead of time. So if you mean like setting some of those to be 0 so that you're not using all of them?
I guess that's future extensions. Thank you.
Yeah, thanks.
So let's thank the speaker again. So the next talk will be presented by Guilherme Franke from Johns Hopkins.
Okay, so you saw 2 nice talks about connections between optimization methods and dynamical systems, discrete dynamical systems, and today I'm going to talk about another connection with dynamical systems, but in continuous time, and specifically for ADMM and accelerated ADMM. This is joint work with professors Daniel Robinson and René Vidal from Johns Hopkins. So over the past few years, a lot of interesting connections between optimization and continuous dynamical systems started to emerge. And if you can relate an optimization algorithm to a differential equation, then a gamma of well-established results from the theory of differential equations and dynamical systems can be immediately applied. For instance, you can use Lyapunov's theory of stability to understand the behavior of the algorithm around critical points. You can also potentially use this to propose new techniques to obtain convergence rates. And these connections may also suggest new algorithms or improvements in existing ones. Perhaps the simplest example dates back to Cauchy, who introduced gradient descent as a discretization of the gradient flow. Here, capital X is a continuous function of time, which plays the role of the discrete iterates. And in taking this continuous limit, you have to make the step size small enough. It's well known that gradient descent has a convergence rate of 1/k for convex objective functions, and it's easy to show that the gradient flow also minimizes the objective function, and this happens at a rate 1/t. Therefore, they have a matching convergence rate. Another example is Nesterov accelerated gradient descent, which is essentially gradient descent, but you introduce these hat variables, and you accelerate the variable through this update. And the acceleration mechanism was considered mysterious, still considered, and many authors tried to understand in several different ways, and a great progress was made by Sue, Boyd, and Candace, who showed that Nesterov accelerated method is a discretization of this second-order system that here I call accelerated gradient flow. It's also well known that Nesterov has a convergence rate of 1/k squared for convex functions, and again, this dynamical system has a convergence rate of 1/t squared, which is optimal among first-order methods. So previous work considered only unconstrained problems and for gradient-based methods. In this work, we're going to go beyond that and consider a constraint optimization problem of this form, subject to this constraint, and for proximal-based methods. More specifically, I'm going to obtain differential equations modeling the behavior of the ADMM algorithm, and also for an accelerated variant, we're going to consider Lyapunov stability for a general convex function and obtain convergence rates for convex functions. So ADMM is given by this set of updates. So we have the two proximal operators here and the update on the dual variable. And rho is the penalty parameter. And our first result is that the continuous limit of this set of updates is given by this first order differential equation, which here we call ADMM flow. You might recall that it's pretty close to the gradient flow, except for this term preconditioning the gradient. Therefore, this result generalizes the previous connection between gradient descent and gradient flow, which is recovered if you put A equals identity here. Regarding the stability, if X star is a strict minimizer and the only critical point in some given region of this objective function, then X star is asymptotically stable. Pictorially, what I mean is stability implies that the trajectory is going to be bounded to be close to the minimizer, and asymptotic means that the trajectory actually converges to this minimizer. Now, if you assume that the objective function is convex, then you can prove the convergence rate is 1 over t, and this is independent of the previous result. Therefore, ADMM is known to have a 1 over k convergence rate for convex functions, and again, we recover the same rate in the continuous time limit. Now, let's consider an accelerated variant of gradient descent, which was proposed not too long ago, and it's essentially the same updates of ADMM, except that you introduce these hat variables and use Nesterov's idea to accelerate them. So the continuous limit of these updates, provided you choose t equals k divided by square root of the penalty parameter, is given by the second order differential equation, where again this term appears preconditioned in the gradient. And if you remember from the beginning of the talk, this differential equation is also pretty close to the one from Su, Boyd, and Candace. Therefore, this result generalizes the previous one, which is obtained in the particular case where A equals identity. Now, because this is a second order system, to consider stability, you need to take into account the position and also the velocity. So if you assume that X star is a strict local minimizer of your objective function, then X star comma 0 is a stable critical point. Now, the system is second order, so the trajectory oscillates, and because it's only stable, there is no a priori guarantee that the trajectory is going to converge to the critical point. Nevertheless, the dynamical system is still minimizing the function, and this happens at a rate 1 over t squared. Now, in the discrete case, this rate is unknown for convex function. It was only proved assuming strong convexity of both terms in the objective, and moreover, that G is quadratic. Therefore, there is some room for improvement in the discrete case here. And let me show you an example where you can recover asymptotic stability for the second order system. If you introduce a so-called forcing function, phi, from positive reals to positive reals, such that for any sequence, if this function goes to 0, it implies that the sequence itself goes to 0. So basically, it says that the function only vanishes at 0. So around the critical point X star, a minimizer, a local minimizer, if you impose this relation, then X star comma 0 is asymptotically stable. What this means pictorially is that the trajectory still oscillates, but the amplitude of these oscillations dies out, and eventually the trajectory converges to X star. An example where this happens is for uniformly convex functions. So I told you the theory. Let me show you just a simple case to convince you that this also works in practice. So the solid lines here corresponds to the algorithm, and the dashed lines corresponds to numerical solutions of the differential equations. Here I pick a very simple quadratic problem. It's a convex problem. To integrate the first order system is trivial. To integrate the second one, the second order one is a little bit more tricky, and you have to write the system in Hamiltonian form and use a method called symplectic integrator. And you can see that the curves of the algorithm and differential equations they match, and the convergence rate from the previous theorem holds. So in summary, we consider a constraint problem, obtain continuous limit of ADMM and accelerated ADMM, convergence rates under convexity, and you consider stability on strict minimizers, ADMM is asymptotically stable, accelerated ADMM is stable, but you can recover asymptotic stability by introducing this forcing function. And our results immediately apply to the previous case of Nesterov and the second order gradient flow if you put the matrix A equals identity. Okay, so thank you very much. And if you're interested, please come talk to us on poster 136.
So we have time for some questions.
Yes, great talk. I've got two questions. So first of all, in the gradient flow, it seems like the rho parameter just does not appear in the limiting differential equation.
Yes, whenever you take a continuous limit, you have to absorb the step size or the penalty parameter in your time. So actually, the continuous time measures your clock is running and depends on the parameter. It absorbs it.
Okay, so I guess my second question was kind of related to that, but so does that sort of mean your theory has kind of no insight or about how to actually set the rho parameter?
Yes, in the continuous time, there is no parameter.
I see.
So yeah, you have to assume that the parameter is actually quite small.
All right, thank you.
Yep.
So let's thank the speaker again. So the next talk will be presented by Pavel Duranchensky.
Pavel Dvorechensky.
Sorry about that. Thank you.
Good afternoon to everyone. The topic of my talk is optimal transport, and this is joint work with my colleagues from Moscow, Alexander Gasnikov and Alexei Krashnin. So we consider so-called discrete optimal transport problem. So this means that we have two discrete probability measures, which are given by vectors R and C from probability simplex. And we also given a cost matrix capital C, and each element of this matrix with indexes I, J says what is the cost of transportation of unit of mass from point I in the support of the first measure to the point J in the support of the second measure. And our goal is to find optimal transport plan, which is given as matrix X, and each element ij of this matrix says what is the amount of mass which we transport from point I in the support of the first measure to the point J in the support of the second measure. So this should be a non-negative matrix, and we also need to have these marginal constraints that if we sum elements of matrix X in a row, then we'll obtain the mass at the point I of the first measure. And the same story is for summing over columns. So, and the problem is to find such transportation plan which minimizes the cost of transportation. So this is given by this linear objective function. So this is a Frobenius dot product of matrix C by matrix X. So this is the total amount of work. And we have these marginal constraints, which mean that we need to transport first measure to the second measure. So why this approach based on optimal transport has become so popular in machine learning is that it allows to based on some ground metric in the ground space. For example, this can be a space of pixels of images to define some new distance between probability measures on this space. So for example, this can be a distance between images. So this is known in the literature as Hofmuller's distance or also Wasserstein distance. So one of the machine learning illustrations, so in his paper, Marco Couturi considered an image classification problem using SVM based on different kinds of distances between images. And he showed empirically that optimal transport distance, so the two bottom curves, so the magenta one is Hofmuller's distance, and the lower one, black, is his modification, which is called Singhorn distance. So they outperform other distances. And the idea is that we have some standard Euclidean distance between pixels in the images, and we lift this distance between pixels up to the space of probability measures, which gives us a distance between images. So let's talk a little bit about the complexity of this problem. So we need to solve this linear programming problem. We want to find an epsilon approximation in terms of objective value. And the important thing is that we want the optimal our approximation for the transportation plane to lie in this transport polytope U of RC. So since it is a linear programming problem, we can use some standard LP solvers, but the problem is that it's quite hard to do it for large scale setting. So for example, if we have 1000 by 1000 pixel images, then n equals to 1 million, so n to the power 3, it's actually unfeasible. So then the state-of-the-art approach to solve this problem was proposed in the same paper by Marco Couturi, and the idea is to add entropic regularization to the objective. So we have this sum of xij's times log xij with some regularization parameter gamma. And last year, Schuler, Witt, and Regalet showed that the complexity of this approach for epsilon approximation of optimal transport distance is proportional to n squared divided by epsilon cube. So the very good point here is this n squared dependence on n. So this is really better than n cube. But the drawback is that we have this epsilon to the power 3 in the denominator, which actually prevents achieving good accuracy. So also entropic regularization have some drawbacks. So for example, it introduces a blurring in transportation plane. So for example, here you can see, so the left picture is non-regularized optimal transport plane, which is very sparse. And we see some blurring introduced by optimal transportation, by entropic regularization. And another drawback was addressed by Blondel, Séguier, and Trollet also last year. And the problem is that actually entropic regularization leads to fully dense approximation for the optimal transport plane. So this is not good for some applications. For example, in image color transfer, sparse approximations for optimal transport plane can be interpreted from the nature of the problem. So instead, they propose to use square Euclidean norm regularization, and they showed that it leads to a very sparse pattern in the optimal transport plane. But the problem is that if we use square Euclidean norm regularization, we cannot use any more Sinkhorn iteration because it's very specific to entropic regularization. So based on that, our goals in this work were first to propose some ways to get better complexity bounds for the epsilon approximation. And second goal is to propose a flexible framework which allows to use other regularization, but not only entropic one. So the first contribution is improved complexity of the Sinkhorn's algorithm. So instead of 1 over epsilon squared, we obtain 1 over epsilon complexity. And also our bound as a byproduct gives a theoretical explanation for very common heuristical trick. So what people do in practice, if they see 0 elements in vectors I and C in our probability measures, they say that for stability reasons, they change the zeros to some small values like 10 to the power of minus 6. So our bound, so it depends on some R, which depends actually on minus logarithm of minimal values of R and C, says that if we do not do that, we cannot guarantee any convergence for Sinkhorn's algorithm. So then we also apply Sinkhorn's algorithm to approximate optimal transport distance and improve complexity for approximating distance. So we now have epsilon squared in the denominator instead of epsilon cube in the previous work. And interestingly, in our experiments, we see still 1 over epsilon dependence for Sinkhorn's algorithm. So this actually leaves an open question. Maybe one can improve complexity analysis of the Sinkhorn's algorithm and obtain 1 over epsilon complexity to approximate optimal transport distance. And our second approach, so we also developed an alternative approach. It is based on accelerated gradient descent. So to do that, we consider a general optimization problem in which we minimize a strongly convex function with linear constraints. So our algorithm is a kind of accelerated gradient descent applied to the dual problem, but we obtain accelerated convergence rates 1 over k squared for the primal objective and for the constraints feasibility. Another important features of our algorithm is that we incorporate light search strategy so that our algorithm actually adapts to the local smoothness of the problem, which gives better performance in practice. And also, we're able to work with entropy, which is a kind of hard function because it's non-Lipschitz continuous, and its gradient is not Lipschitz continuous. So since we consider this general optimization problem, this actually provides a flexible framework for optimal transport problems with different regularizers. So instead of R of x, we can use any other strongly convex regularizer, for example, squared Euclidean norm, and we just can apply our general algorithm and obtain also some complexity bounds. So finally, we use entropic regularization and apply our method to obtain complexity bounds for approximating optimal transport distance. So here you see a long expression, but since it is a minimum of 2 terms, the main term is the left one. And so you can see that we gain another epsilon in the denominator. So we now have 1 over epsilon complexity for optimal transport distance, but not by Sinkhorn algorithm, but by accelerated gradient descent. And also, we perform some numerical experiments and compare both approaches. So for details, you can visit our poster, which is number 117. Thank you.
So we have time for a question. No? So in that case, let's thank the speaker again. So the last talk in this session will be presented by Yang Chen Yuan from National University of Singapore.
Hello, everyone. I'm Yan Chen. So I will present my work with my supervisors, Professor Sun Nefeng and Professor Talking Chen, use the second-order method to solve the convex clustering problem. So this is the outline of the talk, and I will put most of the time on the second part. So convex clustering problem is just solve this very simple problem that after you solve this problem, you can get the clusters by if AI and AGA are in the same cluster, then it's equivalent to say xi equal to xj. So, but you can see that, okay, the model, the second term in the regularizer is quadratically dependent on the number of data points, so it's not that scalable. So many researchers suggested this weighted version. After this weighted version, you can include the following very interesting choice of the weight by KDS labels. Then you reduce the number of the regularizers from quadratical to the linear dependent on n. So in this talk, I will mainly discuss how to solve this problem efficiently. So we can rewrite the problem in the more compact form by introducing some linear operator, and you can write down the dual problem in the following way. And if you solve the dual problem, then you can use some algorithms, for example, the APG or the Freestar to solve. But for our method is to solve the primal problem. And another very important thing for this model is actually the proximal mapping for the L2 norm composite with a linear operator is very interesting in many application problems. So this is the augmented Lagrangian function and the KKT system. And our method is called the augmented semi-smooth Newton CG-based augmented Lagrangian method. So this method, the augmented Lagrangian method, is well known, and you have the fast linear rate convergence rate. But the difficulty is that, okay, if you use the augmented Lagrangian method, your variable x and u coupled together. So, so the key thing is how to solve this sub-problem very efficiently, because when you update the dual variable, it's just a linear equation, right? So for that part, if you look at the function in details, you can see for the variable u, it's just the approximate mapping of the function p. Then we can substitute in back. You can solve for u just the approximate mapping, substitute back, you can get the small phi x. So the important thing is that how to solve this nonlinear optimization problem very efficiently. And you look in detail that phi is a strongly convex problem. So you find the optimizer x star is equivalent to say you solve the first order optimality condition. And we know that this one is differentiable. So our target now is to solve the gradient of phi equal to 0. This is a non-smooth and a nonlinear equation. When you think about, okay, solve the nonlinear equation, then you think about Newton's method. But this guy is not differentiable, so the good thing is semi-smooth. So although it's not smooth, but it's semi-smooth, that's why we use the semi-smooth Newton method. And the method is given by this algorithm. So after you compute the generalized Jacobian, you can solve for the Newton's direction, then you apply the line search to search for your step length. After that, you update one time. And we all know that, okay, the Newton's method can achieve quadratic convergence rate. So that's why you can solve the sub-problem very efficiently. After you solve this one, and the outer loop have a faster linear rate convergence, so you can solve the problem very efficiently. Now the key thing is how to compute the Newton direction. That is the key thing. So many people argue that, especially in the community of machine learning, they think, okay, second order method is not that, you cannot use that for large scale problems, but that is problem dependent. If your problem have some very special structure, although the Hessian matrix is very big, but it's not a big problem. So we look at this problem, you can see that, okay, what we want is that the Newton direction is not the Hessian matrix, right? So if we use the iterative solvers, so the most important thing is the matrix vector multiplication. So you look at the Hessian matrix, although you cannot write down it explicitly, but you can compute the matrix vector multiplication in a very efficient way. And if the alpha ij is greater or equal to 1, then that block is 0. And the whole problem is a block diagonal. So you only care about for those alpha ij less than 1. This is a very important property, and I will show you what this means for this problem. So now we know that we can compute the matrix vector multiplication and use the conjugate gradient method. We can solve for the linear system very efficiently. Then we can get a Newton direction. You apply the line search, you can update once, right? So the very important property, we call it the second order sparsity. The second order sparsity comes from the structure of the Hessian matrix. For those alpha ij less than 1, you need to compute it. For those alpha ij greater or equal to 1, it's 0. You do not need to compute it. And what does that mean? If you choose the weight based on the k-nearest labels, if you solve for the problem, you get an optimizer, then this means, okay, alpha ij less than 1 equivalent to say j is in i's nearest k labels, but does not belong to the same cluster. So you can see that all those points should near to the boundary. And those points should not be very, very big. It's not scalable as much as the number of data points. That's why our algorithm is scalable. So this theorem just say the semi-smooth Newton method have the quadratic convergence rate. And now I show you some numerical experiments. This is some visualization, the clustering results obtained by this model. And we stop our algorithm by the KKT residual. And we compare with the state-of-art solver designed by Eric Chi called AMA. So we stopped because it's an unconstrained problem for the problem. So we just stop, compare the optimization, the function value, and as long as AMA achieved a similar function value as us, we stop it. And here are some time comparison. You can see our algorithm is quite fast and scalable. This is some experiment on the real data set. And you know that you can get the clustering paths that you solve the problem for different value of gamma. And you can see AMA is very sensitive to the gamma. And our algorithm looks quite okay to the gamma. And if we look at the scalability, okay, our algorithm almost linearly dependent on the number of data points. So in conclusion, why our algorithm is scalable because the structure of the second order sparsity, and because the outer loop is a fast linear convergence rate, and the inner problem have the quadratic convergence rate. That's why we can solve it very efficiently. Thank you very much.
So we have time for some questions. So maybe I have one. So how does that scale with the dimensionality? With the feature dimensionality?
Oh, feature dimensionality. Okay, I have an example here. In the left is scalability with respect to n, the number of data points, and on the left is scalability with respect to d, is the dimensionality on the right.
So any other questions? So if not, let's thank the speaker again. So this concludes our first session. So let's move on to the second session on convex optimization again. So there are 5 talks in this session. So the first one will be presented by Mikhail Balkin from Ohio State.
Thank you. So I'm going to talk about the work we have done on understanding why stochastic gradient descent works so well in modern machine learning, and this is joint work with my students, Yuan Ma, and with my colleague from Ohio State, Raif Basili, who did fantastic work on this, and unfortunately none of them could come because of the visa issues, either getting a visa to Europe or going back to the US. It's a real disaster. I feel have to do something about that. Okay, so let me first point out that, so in machine learning, the usual machine learning problem, we typically, at least in sort of modern large-scale problems, we use large-scale optimization method by doing empirical risk minimization. And empirical risk minimization is simply minimizing the function over some class of functions, like neural networks with certain parameters. And the way it's done in most machine learning applications is using stochastic gradient descent. The kind of natural question to ask here is, well, if you know a little bit of theory of stochastic gradient descent, it's supposed to be slow. Yet it seems to work extremely well in modern machine learning. So what's going on? Why is stochastic gradient descent so fast? That's basically the question we're trying to answer here. Now, if you sort of, the first observation to make here, and the point we're going to take, is that in certain regimes, stochastic gradient descent is not slow at all. And these are the regimes which actually occur in modern machine learning. Let me first describe interpolation for you, just to be on the same page. So interpolation for me, and I'll talk a lot about interpolation. So it's just finding a function which goes exactly through my data point. So that means that the loss is 0. And you can view it as L2 loss being 0, okay? My function fits the data point exactly. Now, in most practical applications, you don't actually run all the way to convergence, so you may have some weaker versions of that, like, for example, 0 loss fitting, when the sign of each point is correct. Now, this is a very typical situation, what we observe in machine learning, or what many people observe in machine learning. This is one example. If as you train your method, so this is the number of epochs, your training error goes down to 0 and becomes very small. And your test error, it goes down first, and then it stabilizes, and it never really goes up. And that's kind of an interesting phenomenon. I'm not really going to talk about generalization here. The fact is, we can go down all the way. We can train as long as we want. And the test error sort of is very good. And in fact, this is a kernel method, we can push it much further. We can solve this problem directly. So we can interpolate by getting something like 10 to the minus 27 loss on the L2 loss on the training set. And that still is very good. That generalizes very well on the test set, as well as the optimal values of parameters. So taking sort of this point of view, and really we have seen this in a range of methods in machine learning, from deep neural networks now, kernel machine, well, way back, random forest and other burst. But let's take this as a given, and let's see what the implications of this are for convergence of stochastic gradient descent. So let me very briefly remind you what stochastic gradient descent is. So basically, we're trying to optimize a function, L of W, and this is my total loss over some set of parameters W. And since this function is a sum over individual data points of something like this, well, so for example, for a square loss, it would be that, I can try to, instead of optimizing this whole loss, so instead of doing full gradient descent, I can do gradient descent kind of one term of the sum at a time. That's a classical idea of stochastic gradient descent. And you can do it one at a time, or you can use a mini batch to do it m at a time. Now, the theory of stochastic gradient descent, and this is for convex functions, it tells us that stochastic gradient descent gives you a rate of something like 1 over t, where t is a number of iterations. On the other hand, gradient descent gives you e to the minus t, right? That seems to be a lot better, right? Of course, stochastic gradient descent is cheaper since you're only doing it one at a time, but since this is much, much worse. So why use SGD? And there have been some answers that it somehow relates to non-convexity, but actually it can be explained in a fully convex setting. The fact that SGD is preferable to GD. And you know, frankly, all major neural network architectures use SGD. Nobody uses full gradient descent. SGD or variants like momentum and so on. Okay, so what's going on? The intuition is really quite simple, and once you sort of believe that this interpolation phenomenon happens, which I had in the slide before, I can describe intuition in basically one slide. So first, the key observation is that suppose I am in the interpolated regime. What does it mean for me? That means that there is some value of parameter W star such that f of xi is equal to yi, and that is equivalent to the fact that each of these losses at every data point are equal to 0. Actually, the fact that they're 0 are not important. The important thing is that they're minimized at the same point at W star, all of them simultaneously. And that is enough to imply exponential convergence. And let me go over a really simple example which sort of describes this. Take the following quadratic loss function, which you can think of just having two data points, 1 and minus 1 and 1 and 1. And there is one parameter. So of course, you cannot have interpolation here since there is no value of parameter which minimizes both of these guys at the same time. So if I am to do stochastic gradient descent for this function, what I'm going to do? Well, first I'm going to be presented with this one. I'm going to take a step left. And then I'm presented with that one. I'm going to take a step right. Left, right, left, right, right? I will oscillate. So without doing something a little bit more clever, like taking adaptive step sizes, or maybe doing averaging or doing some other thing, I will never converge. So for example, fixed step size doesn't converge in this situation. Now, let me modify this problem very slightly in a small but important way. I am splitting this W into two variables, and I have almost the same problem, but now there are two variables, W1 and W2. And of course, now there is a solution which minimizes both of the things simultaneously. It's simply W1 is equal to 1 and W2 is equal to minus 1. Now, if you think about it, stochastic gradient descent will do alternating gradient descent in directions of W1 and W2. And you will have convergence, which is exponential, because you are basically doing gradient descent, but separately in those directions. So you don't need adaptive step size, you get fixed step size exponential convergence. Okay, well, this of course is a very simple example. You can formalize it, and this is the theorem that you can get. That's what we get. So if you have a convex log function, it's lambda smooth, alpha strongly convex, and Li are beta smooth. I'm not going to go into the details of the definition. You basically have exponential convergence of SGD with a mini batch size, and the rate is exponential, well, clearly. So this is the error after t steps, and after t plus 1 steps, and there is something here in terms of t, and you can in fact choose a step size which is constant and sort of nearly optimal. And there is related work for m equals 1. Well, really, first work was Strom and Vershinin when they showed randomized Katzmart's method, which is very closely related, shows exponential convergence for the quadratic laws. And Mullins and Bach and Nidell, Schreber, and Ward, they had a generalization of this result for m equals 1 to other loss functions, non-quadratic. Okay. So let me give you one implication of this, which is kind of interesting because you're getting something for free here. What are you getting for free? Well, there has been quite a lot of work on trying to make stochastic gradient descent fast. And you do it by various clever techniques, and it's a rather complicated analysis with methods like SEG or SVRG or SAGA and several others. And it turns out that you can simply take stochastic gradient descent, and as long as you're in interpolated regime, your convergence rate is actually better than all of them, with the exception of Katusha, which also uses momentum term. So you're getting this very fast, well, exponential convergence, or linear, if you like that kind of language, for free, just because you're in the correct regime. Now, if you now sort of would like to connect it a little bit more to practice, what we like to run those algorithms on GPUs. And GPUs basically can do mini batches, or at least reasonably small mini batches, very fast in parallel. So you have 4,000 tiny little processors, and you can do matrix multiplication in basically one step on them. So what happens with M when you change the mini batch size M? Basically, you go from 1 over beta to 1 over lambda, and that's when M equals 1, and this is 1 over lambda when M equals beta over lambda. And I'll describe this in a little bit more detail here. So what do we have here? We have, as we're changing M, we have basically two regimes. One regime is what you may call linear scaling, when M is smaller than M star, with M star being this quantity, beta over lambda. And in the linear scaling regime, one step of SGD with mini batch size M is equal to M steps of sort of standard stochastic gradient descent. When, of course, when I say equal, it's not exactly equal, it's close, within a small, actually it's close to, the constant is close to 1 here. Now, when M becomes bigger than M star, you get saturation. And there, one step of MSGD becomes more or less equivalent to one step of full gradient descent. And there is another constant here, which is like 4, relatively small. So going beyond this, you somehow don't really get very much. So it's a diminishing returns type of regime. So that's, if you kind of think of this being the number of steps of SGD that you need, so that's kind of the graph you get. Up to M star, you get linear, and after that it saturates and becomes flat. So even going to the full data size doesn't really make a big difference here. Now, for the quadratic loss function, M star can be understood very easily. It's basically trace. It's not exactly trace, but it's a good approximation. I don't want to define it exactly what it is, but you can think of it as being trace of the Hessian divided by lambda 1. And what's cool about this? The really cool thing about it, if you think about that, this is more or less data independent, right? As you get more and more data, your trace divided by lambda 1 doesn't really change. They converge to something. So that means that stochastic gradient descent have O of n computational advantage over gradient descent. It is provably better and much better, especially when n is large, as the case in practice, like you have ImageNet with 1 million data points. Okay, so now for the quadratic case, for the quadratic loss, this analysis can be made very precise. I don't want to go over the details here. But the interesting thing here is that the mini batch of size 1 actually turns out to be optimal. But really, the difference up to m star is very small. So even though 1 is optimal, you can go to 2, 3. It doesn't really make a big difference. So you have a linear scaling, but it is just slightly sublinear here. Okay, but m star is kind of the limit of effective parallelization. So let me give you one example of this. And this is for specific for a kernel method with a Gaussian kernel, when we can actually figure out exactly what those quantities are. And it turns out that we know roughly lambda 1, what lambda 1 is, beta is equal to 1. So we can actually estimate m star precisely. It's very close to 8. So what do we see? We see here, so this is kind of mean squared error after that many epochs. And epoch is just a fixed number of computation in the sequential model. So you can see that m equals 1 is the best. But m equals 8, which is a critical size, is only slightly worse than m equals 1. And that's exactly what we expect. When m goes to 16, you get slightly worse than 8. And if you go to, say, 128, it's much worse. So you see that per computation, really you are getting very good results from these small values up to m star. Or slightly more than m star, it's still okay. But interestingly enough, parallelization beyond m star equals 8 will have very little effect. So 8 is basically how much you can parallelize that. Okay, so that's the example, and that sort of follows pretty closely to what we would expect from theory. Now let me discuss how it actually happens in modern machine learning. And I'll ask you, well, suppose I want to interpolate. Well, how would I do it? What do you do to interpolate the data? Well, you say, well, suppose, let's just think about the linear system, right? Ben Regger gave a very nice tutorial yesterday. He said about, let's understand linear first. Well, this is a good example of that. How would you interpolate with a linear system? Well, you have to have enough variables to solve the system exactly, right? So the number of variables better be equal to the number of equations, so the rank works out correctly. And if I have even more variables, then that makes my job to interpolate easier. So basically, I can interpolate, roughly speaking, whenever my number of variables is bigger than the number of equations. So you can kind of think over parameterization makes it easier to interpolate. And now, it's actually true even for non-convex set, because if you think about it, it's basically the same. Of course, it's much harder to prove, and to prove it mathematically rigorously requires a lot of work. But the intuition stays the same. Now, if you look at the modern architectures, these circles, this is from Kanzani et al., these circles are various neural networks, and this is the size of the circle is the number of parameters. They all have from 5 to 150 millions of parameters. So the number of parameters is much larger than the number of data points. So they're very, very heavily over-parameterized. And in fact, Ras Sologdinov gave a nice tutorial on deep learning at Simon's Institute last year. And this is kind of the best practice in machine learning, in deep network. You build a very big system, and you basically want to make sure you hit the 0 training error. So that's how you interpolate, right? You make a very big system, and you run it to get it very close to 0. And then you get something like this. So this is from Zhang et al. You get accuracy 100%, and you see that generalization works well. So that's basically what we have. Modern machine learning aims to interpolate. Now, you can kind of view it as systematic over-parameterization. The number of parameters is much larger than the training data. And how much computational advantage do you get by that? Well, if you think about it, your n may be 10 to the 5 or 10 to the 6, right? About a million data point kind of data set. And so that gives you about of 10 to the 5, let's say 10 to the 5 advantage of a gradient descent. And now if you put it on GPU, it maybe you get another factor of 100, let's say. acceleration, so you get overall 10 to the 7 factor of gradient descent on CPU. So SGD on GPU is 10 to the 7 times faster than GD on CPU, right? That's a huge factor. That's like the Moore's law. And you know, we used to do this not so long ago, just a few years ago. Okay, so maybe I can have a couple of final slides to summarize. So that kind of, you can view optimization in modern ML. You over-parameterize it heavily. This leads to interpolation. Interpolation results in fastest GD, at least in the convex case, it's probable. And then you do it on a GPU, you run it on a GPU, and that gives you another acceleration because you can do mini batches basically all at once on a GPU. Now, there are a couple of things which are kind of, you can say, well, there are some things missing from this picture. And one thing is, let me sort of call them next steps. Our analysis is convex, but deep networks, of course, are non-convex. So how does that square? Well, so maybe the intuition here is that perhaps non-convexity is not essential when the number of parameters are large, and we're sort of now trying to understand it theoretically. But it's enough to have enough directions in which kind of convexity happens. So if most directions kind of go down, you may not care so much because you have so much freedom. So, and that's one. And the second one, I'll leave you with this cartoon. There is something very important aspect of this is missing, and a miracle occurs. What about generalization? And I'll sort of use it as a plug for maybe for the work we have tomorrow. That's a very important point. And thank you.
So we have time for one quick question. So if not, since we have run out of time, so maybe let's thank the speaker again. So the next talk will be presented by Minhao Zheng from UC Davis.
Hello everyone. So hello everyone, I'm Minhao, and my topic is fast variance reduction method with stochastic batch size. This work is done by Shenqing and Chou, but they couldn't come because of the visa problem, so I will present their work here. Okay, so let's start. So first, we are considering classical empirical risk minimization problem, but we have the assumption that the Fi is mu strongly convex. So basically, traditionally we are solving the problem use the normal SGD, but actually the SGD cannot utilize the modern hardware very well since we are getting more parallel power now. So we are using a mini batch SGD instead. So the mini batch is simply just averaging all the SGD result. Okay, so, but there is another topic that we are using today is we use the variance reduction method in the SGD. So what about we can further reduce the variance of a gradient? So this is the basic framework of the SVRG the saga. And the power of them is actually they have unbiased estimation. Also, the variance is negatively correlated with the gradient is negatively correlated with the GK here, which means our variance is always reducing. And there is showing that there are chosen by some great step size, we can always get a very good convergence result. So, actually this problem didn't utilize with the batch settings, which means we can also use the mini batch settings as well. And you can see now the power of our computing resources is getting bigger and bigger. And but we do not use the batch size or the mini batch strategy in the SVRG or variance reduction method. So we are now our topic is how to get a good batch size for the SVRG method or Saga method. So we here proposed the Saga++, and which is based on the Saga. And you can see the basic framework is the same with the Saga. Only difference is we have a batch size chosen here. So the problem becomes how we choose a good B to get a very good convergence rate. So now our strategy is actually we are sampling from the we are not using the fixed B. Instead, we are using sampling to choose a B. So which means if we set the B, the probability of B equal to n as 1, which means we are always using setting the batch size to n, which is the gradient descent. And if we are setting the beta B equal to 1, then it is basically the Saga. But now our setting is we are taking the expectation over the B to equal to some related B, so we can get the convergence rate related to the B we are choosing the expectation. Okay, so the main result as follows. So we can choose B with some carefully chosen ET, which is the step size, and we can get the convergence rate to 1 minus rho t times. And now our problem becomes to achieve those convergence rate, what B we should choose from. So we are actually optimizing or minimizing the B divided by rho B instead. In our paper, we have shown that B equals 1 is optimal, which means that the Saga is always the best, but it is still and this result is. But another paper has shown similar result is for the mini batch SGD. So which means the SVRG we are always choosing batch size 1. We are get the best convergence rate. But another way, the convergence rate doesn't represent everything. So if we want to use in the practice, now we are considering the running time instead of the convergence rate. So the running time matters. There are several key components that will affect the running time, which is first as we all know that first when we want to do the optimization or do the machine learning, then we first should go get the data from the memory devices and get to the RAM, get to the cache, to the CPU. But actually, if we choose in the randomized exercise, then if in certain scenario the speed, the training speed or the reading speed will be very slow. So there are 3 scenarios. So first is if the data is mainly stored in the memory, and also the data is too large to fit in the memory. Also, even if the data cannot fit in the single disk, we use in the distributed system. So in those scenarios, the random access will be very slow compared to the serial access. And we have, those three are very common used very big large data set, and we can show that the sequential reading time is much smaller than the random accessing time. So it will bring a problem that if the sequential time divided by time t, eta and eta we call here is the cache ratio. If the cache ratio does affect the running time, which is not shown in the convergence rate analysis. So this collapsing is certain complex, and you can just refer to the paper refer to the paper if you want to know the detail. So, but we have a more explicitly show that so the eta is the cache rate I mentioned before. So with a strong effect on the cache ratio, then we should choose a bigger batch size compared to the previous way. So if the cache ratio is not so good and with a perfect condition number, then we can choose 1 as our optimal batch size. But if the cache ratio is small, then we should choose a slightly larger batch size, get to the best performance. And we are doing experiments on the 2 problems listed here, the L1 regularized logistic regression and the L2 regularized logistic regression. And we also compare the results using different data sets. And we have shown that the regularization parameters matters. And you can see the result from here. So the first line is the regularization parameter effect. In fact, this is L1 regularized logistic regression, and this is L2. And these two are measured with different choices of the regularizer parameter. Our method is always good, always the best among those methods, and even with different data sets, we can achieve the same good result. And that's it. So, any question?
So thank you. So since we are behind schedule, so let's move the questions to the poster session. So let's thank the speaker again. So the next talker will be by Martin from U of Connecticut.
So I'll be talking about stochastic gradient descent and Hogwild, and we analyze its convergence without the bounded gradient assumption for diminishing step sizes. So this is joint work with Lam, Ha, Peter, Katja, and Martin. So what do we want to do? So we want to minimize an objective function expressed as the expectation over component functions. And we assume that the objective function is strongly convex and the component functions themselves are both smooth and convex as well. Now for the solution W star of the objective function, we have that the bound that we see here, that capital N, which is defined as 2 times expectation over the second moment of the component functions in W star, that this is finite. Now, what do we not assume? We do not assume the bounded gradient assumption, where we actually assume that for all W, this second moment is bounded. And why? Because this contradicts strong convexity. So if you look at the derivation, we notice that FW minus FW star is actually finite under the bounded gradient assumption, and together with strong convexity, we will then conclude that W minus W star, its norm, is also bounded, hence W must lie in a sphere around W star. Now, of course, we may assume that the bounded gradient assumption holds in a convex set S, but we can only use this if we know a priori the W star is in S and our algorithm is adapted to project back into S after each iteration step. So our analysis does not need to assume any bounded gradient assumption, and we just take S to be the whole space. So for stochastic gradient descent with diminishing step sizes, we see that we have a learning rate every single iteration. We choose one step size. We select a random component function corresponding to the random variable psi t. We compute a stochastic gradient and then compute a new iterate. So let us look again at what happened with SGD with this particular example. Take this strong convex objective function with component functions half W square and W. Then with probability 2 to the power minus t, we notice that the first t iterations actually select F2, and therefore the SGD algorithm computes Wt plus 1 as W0 minus the sum of the previous step sizes. Now this implies that SGD can go arbitrarily far with non-zero probability, because SGD wants to be able to reach any possible W star, and therefore the infinite sum of all the step sizes is infinite. Okay, so what do we want to do? So what we can prove is this particular recurrence, where we see here capital N in the recurrence. That is our bound, right, on the second moment for W star. So with this particular recurrence in mind, we can prove this theorem that states that for step sizes up to 1 over 2L, and the sum of the step sizes is infinite, as discussed before, while the step sizes are diminishing down to 0, because we need to assume here that the sum of the step size squared is less than infinite, then with probability 1, we see that the convergence rate goes down to 0, but we do not really know the rate of the convergence. So let's take the expectations completely through this recurrence iteration. Now we can talk about the expected convergence rate. Now a similar recurrence has actually been proven for smaller step sizes in Moulin and Bach in an earlier paper, but we are going to use this particular recursion because this allows us to state an explicit sequence of step sizes that is diminishing and starts off with an initial point 1 over 2L, and for t large enough we get that the expected convergence rate is upper bounded by this expression that you can see on the slide. Now both theorems actually hold also if we only assume smoothness of the component functions and not convexity at all. In that case, we just replace L throughout by L times kappa, where kappa is the condition number L divided by mu. So let's take what we have learned to hog wild. So again, we want to analyze this with diminishing step sizes, but now, since we have this asynchronous setting, writes to and reads from vector positions in shared memory are inconsistent. So our analysis again does not use bounded gradient assumption, and we note that Leblanc and others in February 2018 wrote a nice ePrint that talks about analysis of hog-wild with fixed step sizes, also without a bounded gradient assumption. So we consider again the general minimization problem, and an adaptation of our results again hold by replacing L by L times kappa if we do not assume convexity of the component functions. So what are we looking at? So up here we see general recursion, but let's first not consider the gray area. So then the recursion without parameter D and the matrix S is actually the hog-wild recursion. What do we have here? We have here the W hat T represents the vector that is used in computing the gradient. And its entries have been read one by one from an aggregate mix of all the previous updates that led to Wj in previous iterations. So what's happening here is we have many different cores. Each core, out of order, asynchronously, is reading and writing vector entries. And that's the reason why a current core who's going to do the tth iteration will read a mix, where each entry may come from a mix of updates that have happened before. What do we assume? We assume that W hat is consistent with delay tau, meaning that it includes the aggregate of all the updates to and including the t minus tauth iteration. In other words, all the previous updates before the t minus tauth iteration have all committed properly in shared memory. Now, what about this gray area? The second and third bullet point and the more general recursion formula? Well, we can have a lazy Hogwarts where we actually are going to just consider a subset of the non-zero entries of the gradient and only work with those in our update rule. So here S represents a masking matrix, and our theorem that we have on the next slide actually holds for the general recursion. Here the step sizes have a similar shape, similar form, and now we have that both the expected convergence rate for WT, but also what we read from memory W hat T, is at most this expression. This expression uses T prime, which is the expected number of single factor entry updates after T iterations. If you would express this in terms of T, we would get something similar for pure Hogwarts as what we see with SGD. Now, here, delta bar is actually something that relates to the chosen masking matrices that I just talked about in the general recursion. What do we notice? The alpha t can actually be chosen here such that the step sizes are decrementing after exponentially increasing time windows. And that makes this particular step size sequence perfectly fitting the asynchronous setting of Hogwarts. What we also notice is that the leading term is actually dominating all the other second order terms, even if tau is made a function of t, as large as square root of t divided by ln t. For t large enough, that is again a function, now a function also of sparsity. Now simulations actually confirm our results. For logistic regression, for two experiments, we see that indeed for circle tau, we see very little effect or no effect at all. So thank you so much, and I hope you can come to the poster.
So we have time for a question. So if not, then let's move on. And thank the speaker again. So the next talk will be presented by Shai Zheng from Hong Kong University of Science and Technology.
very sorry about it. Hi, I'm Shuai Zhen, and this is a joint work with James Kwok. And I will talk about paper lightweight stochastic optimization for minimizing finite sums with infinite data. So in machine learning, we are interested in minimizing empirical risk minimization problems, which is a sum over n loss functions with a localizer G here. So we assume that the model actually has linear structures. And we assume that this phi here, the loss function, is a convex function. And G, the localizer, is a smooth convex function, such as the L2 localizer. And one very common optimizer to solve such problem is SGD, but it has very slow convergence. And recently, there are a number of papers called variance reduction method. This can, by exploring the finite sum structures, they can achieve faster convergence rate, such as linear convergence rate for strongly convex functions. And the instance of the variance reduction method include the SAG, SVRG, Saga, and MISO. And they estimated actually the instances of this blue equation here. So here the x is the stochastic gradient, and the y is the control variate. And in this equation, we need to compute the expectation. So this means for variance reduction method, the expectation needs to be evaluated. But in machine learning, we are more interested in some random noise to the data. And it can be used in many domains, such as the image classification, image denoising, and it can provide some kind of regularization, such as adaptive regularization for the linear model, and it can stabilize the predictions, and it can defend the adversarial examples. And more importantly, it can improve the generalization performance. And it can also use for like the data augmentation. And in this picture, you can see we have a cat, and we can rotate the image and to provide like more training examples. So the problem is with the random perturbation, we have a new objective here. The new objective has the expectation over the random noise C here. And this random noise, such as it can be the dropout noise or adaptive Gaussian noise. And here we assume that the perturbed data here, the x tutor, actually is a function of the x, the feature vector x, and also the random variable we see here. The example includes like the element-wise product between the random noise and the feature vector. This is actually the dropout. So the problem is when random noise is added, the problem we actually have the infinite data. And this means we cannot compute the expectation, and the existing variance reduction method cannot be used. And the finite sums actually, its assumption fails. So to solve the objective with random perturbation, the one very common method is SGD. So at each iteration, we sample index IT, and we also sample a perturbation C here, and then we do the gradient descent update. And another recent paper is called stochastic MISO. And similarly, it's sample the index and the perturbation, but to achieve a faster convergence rate, it stores a table of size like n times d, where n is the number of samples and d is the feature dimensionality. And for each sample, we have a z, which can be like a surrogate of the parameter. And by sample index, then we update is z parameter here, and then we take the average, and then we finish the update. And it can achieve the faster convergence rate, but the problem is it requires additional, big O ND storage, and it cannot be avoided even for the linear model. And in our paper, we explore the linear model structure. This means for linear model like these loss functions, the gradient consists of two components. The first one is a derivative, and the second one is the feature vector. And here, the feature vector determines the gradient direction. So in light of this, we proposed a control variate which decouple the derivative and also the feature vector. So here we have a new control variate, and for some AT here, the AT may depend on the past information, but it does not depend on the sample, the index IT. And here is our new proposed gradient estimator. And so here we have, we need to compute the expectation of the feature vector. But luckily for many types of random noise, this one expectation can be computed, such as like for dropout and additive Gaussian noise, the expectation of the corrupted features actually just equal to the original feature vector. And the next step is construct the AT. So to construct AT, we consider minimizing the variance bound. So by minimizing the variance bound, we have the optimal AT here. But the problem is this expectation cannot be computed. Then we consider approximating this AT by moving average. So from this moving average, under certain conditions, we can prove that this AT converge to the optimal value with probability 1, and also it has kind of from the convergence rate of 1/t 2/3. And this is our whole algorithm. You can see it does not require additional memory, and it also requires one single gradient variation in each iteration. And we also propose another algorithm. So, because in the previous algorithm, we used a single AT for all the samples, but it may be better to use the AT for each samples. This means we can, this depends on the saga. So here you can see that for each sample xi, we have a AIT, and we also update the expectation by this simple step. And this algorithm actually reduced to the saga when the random noise is removed. So now let's take a look at our convergence analysis. So we make an assumption on the this term, which is actually the square difference between the derivative and our control variate estimator here. So by assuming that this term is smaller than some constants, we have a convergence rate of 1/t. And also we provide a conversion analysis for S-saga. And similarly, we have a conversion rate of 1/t, and it has a different variance constants. And we can compare the variance constant between S-saga and S-meso here. For S-saga, our variance constant depends on the difference of the derivatives. But for the S-meso, its variance constant depends on the difference of the gradients. So this is, what does this mean? This means if the derivative difference is small, then our variance constant is smaller. This is particularly true for many linear models, such as the logistic regression or the smooth hinge loss. Such as for the smooth hinge loss, the derivative is actually is constant in some regions, and for logistic loss, and the derivative is nearly constant in some region. And here is our experiment result. We performed the experiment on the logistic regression using a CTR dataset with millions of samples and features. And we varied the regularization parameter. Here you can see with different regularization parameters, S-saga performed the best. And SAG and S-meso have very similar convergence behavior. And we also tried varying the dropout rate here. And you can see the S-saga is very robust to different noise levels. And it always performs best. But in contrast, the S-meso can be much worse when the dropout rate increase. So here, in conclusion, we explore the structure of the linear model. And we proposed two algorithms with the very novel control variate. And we have faster convergence rates as well as the lower memory cost. And the method is very robust to varying the condition number and the noise level. Yeah, thank you.
So we have time for a question. So if not, perhaps you can ask questions during the poster session. So let's thank the speaker again. So the last talk is presented by Kai-Wen Zhou from the Chinese University of Hong Kong.
Okay, my name is Kai-Wen Zhou. I'm a master's student from SVRG, and this is a joint work with my supervisor, Professor James Chen, and Professor Fanhua Sheng. And our work is about accelerate the SVRG. As we can see here is the acceleration roadmap given in the chronological order. And in fact, I found maybe the problem definition and finite sum structure and problem assumption is already given by previous talk, so I won't elaborate them here. In fact, most algorithms shown here is introduced before, like the catalyst and the APPA, elaborated by Mr. Alan Zhu in his video. In the previous session, is using some reduction techniques that they want to migrate the acceleration idea from deterministic case, namely the natural momentum, to the stochastic case. So they treat VR method like as an oracle and iteratively call them and combine it with natural momentum to yield an acceleration. And as pointed by Alan Zhu, such an acceleration is not very practical. Yes, and there's a notable variant, it's called point saga. It's the proximal point variant of saga. And its acceleration is achieved by using a very large step size because it requires the exact proximal oracle of the objective functions. We can use, it allows us to use a very large step size. But it's not a very practical algorithm because the exact proximal oracle is hard to compute. Often we only have the approximate proximal oracle. Like even for the logistic regression, we need to run an individual Newton step to evaluate the proximal oracle. And then we have the notable work, the Katyusha from Alan Zhu, and he has elaborated it thoroughly previously. It's a mixture of natural momentum and negative momentum, and it yields a direct acceleration of SVRG. So our work is a step further. A step further is we accelerate using only the negative momentum. It sounds a little bit counterintuitive in its design because it's negative, but we achieve acceleration. If we combine the illustration from Alan Zhu, then things can be more counterintuitive because it seems like we are keep retracting the iterate back, but it accelerates the whole process in a general sense. And I also put a question mark here because the direct acceleration of SAJ is still unknown. Okay, let's go directly to the algorithm. As you can see here, our algorithm is very simple, except for it's very similar to SVRG, except for 2 or 3 steps. The first one is the key coupling steps. We form a convex combination with the iterates, and the snapshot point, it is known as the negative momentum trick. And thanks to the snapshot point, it's a constant point in each inner loop, so this combination can be formed whenever used. So we only need one variable vector update. So our algorithm is very simple, scalable, and it allows for an efficient asynchronous and sparse variant. Because in such a setting, the vector is stored in the shared memory and updated asynchronously. So the less vector we stored, the smaller the variance, the smaller the asynchronous variance we have. and it gives us convenient to analyze it in this setting. And there's a fancy update. It's the weighted average scheme as in Katyusha. In fact, it's an average of y, but as I said, we can compute y whenever used. So we do not need to explicitly store y here. And in fact, our work can be regarded as a simplification of Katyusha. And I will show it here. First, we have the key coupling step in Katyusha. It's a 3-point coupling. This one is given in the notation of the original work. And y and d here can be regarded as the natural momentum. It's called linear coupling in another work. And x tilde here is the negative momentum. It's called Katyusha momentum here. And what we do is we remove the natural momentum, or we break the linear coupling framework here. And this comes to our coupling step. And theta can be regarded as tau1 in Katyusha. And it is proven to enjoy the same accelerated iteration complexity as Katyusha. And as we can see here, the square root of kappa n, kappa is the condition number, compared with merely kappa for non-accelerated algorithms. So when kappa is very large, there should be a significant improvement. So I'll give an experiment here. So it's an air conditioned problem because we normalize the data set and we set a very, very small regularizer. So it's an air conditioned problem. As you can see, there are significant improvements of Katyusha and our algorithm, namely MIG with SVRG and ACC proxy SVRG. In fact, we want to show more things other than this improvement. We want to show a comparison of momentum here. As we can see, the full algorithm is just SVRG and with any combination of these two different types of momentum. And it shows that seems like natural momentum does not improve the performance very, very much. The negative momentum takes the key role in this acceleration. And the ACC proximal SVRG, we use 1 mini batch size. It's analyzed in the Nintendo's work that it requires a large enough mini batch to achieve acceleration. When mini batch is set to 1, there's no acceleration effect. That partially explains natural momentum is maybe not very effective in the stochastic scheme. And I've just learned that 1 mini batch is the optimal choice from the stochastic batch size. That paper, that great work. Okay, yes, only limited improvement shown. Finally, about the question mark in the first slide, it can be shown that even we don't have a constant snapshot point, we can migrate the negative momentum idea to SAJ as well to yield a direct acceleration. And yes, that's our discussions are welcome on the poster session. Thanks.
So we have time for some questions. So maybe I have one. So is your method faster than Katyusha in terms of the running time?
In fact, as shown here, running time is faster, but admittedly, we are using the numerically similar parameter setting because I just don't know how to give a fair comparison because we theoretically analyze one parameter setting, but in practice, we always make parameter tuning, right? So here, the parameter is set theoretically and theoretically feasible and numerically similar. So I think that may stand for a fair comparison, and in fact, in practice, someone may think because we are simplifying Katyusha, so Katyusha has more potential. Maybe he will always achieve a better performance, but in fact, our running time is faster in this experiment, but I don't show here. I think what we are showing is maybe the effective part of Katyusha is the negative momentum. That's what we want to show. But if it's very practical, it's another question, I think. Yes.
Thank you. So this concludes this session. So let's thank all the speakers again.